last week on like these log function parts, and we tried to establish a good way to make the parent function. So we established the parent function. Sorry, I'm flipping it all around and it keeps resizing. Okay, so we established the log parent function. You guys kind of had two ways to come up with these. Way number one was you were just really comfortable with logs. And when you like saw log base 2, you were fine with understanding these were the x values. Okay? Other way was you went back and you built the exponential function, and then you just inverted it, switched the x's and y's so you could have the log function. So if you're uncomfortable with logs, you want to deal with exponential functions and then kind of invert them and use the x's and the y's. Okay? All right, so once we built these, what we didn't do is we didn't go through graphing with the transformations. And really here, the parent function is going to be the thing that's significantly different because all the transformations are going to work the same way that they have before. So we're going to do one example together with a lot of transformations. We're going to look at number 3, and then we're going to let you guys work on homework 7, and I'm going to give you guys classwork 5. It's like one more piecewise handout, but this time like log and exponential functions could show up in there as well. So when you look at this function, the first thing you should notice is that it has the logarithm in it, and then you should build the parent function so you have that starting table. So again, you're either really good at recognizing log base 2 and knowing that you'd want to use powers of 2. So the 0 power of 2 is 1. Then they get bigger this way. They get smaller this way. I know that because I'm relatively good at logs. I should be, right? Like I do them every year and all this kind of stuff. But if I'm not comfortable with logs, you would have done like a pre-step to this. And kind of your pre-step would have been to build an exponential equation instead. Sorry, because you're uncomfortable with logs. Really, I just did something fancy. Okay. And so your pre-step would have looked like this. You would have built the exponential function. So you would have used 2 as the base, raised it to these different powers. And then you would have just flipped it around. So these y values become your x values, and then the x values become your y values that go with those. Okay. So either you know how to get the x values because you just understand log and you know which values go with them, or you don't, and you do this little pre-step with the exponential function. Okay. Do not go back and use this again. If you did this pre-step, you need to recognize that normally in all these graphing problems, you guys build 2 tables. One table with the parent function, and then one table with the transformations. So don't stop here. This was something you don't normally do, is build an extra table. Don't really use that in the problem. Okay, now you need to forget about it. So this was your parent function, and now you need to get your transformation of that function. Okay. The other thing to remember about logs, because it will help you with your graph to see if you did it right or not, is to remember that they have that vertical asymptote at x equals 0 for the parent, because you'll want to plot that with your points. Sometimes that helps show you if one point was off or if they're following the right direction and some things like that. Okay. All right, transformations. Main idea for people that need help with transformations. Remember, you need to look at your x minus h value separately from your b value. So I don't want to think of my h value as coming from 4. Instead, I want to think about it as 2 because of what this looks like right here after it's been factored out. Okay. So horizontally, what's happening to x? There's this b value of negative 2. Okay. What am I going to do to calculate where that's moving points on the graph? What am I going to do to x? X is going to have to be negative because it's getting changed sign there. And what should it be multiplied by? 1/2. Good. We're always using the reciprocal of the b value. Okay. And we went through charts and graphs and saw why that happens like that. Then in here it says x minus 2, but remember that's your x minus h. The minus is part of the formula. The h value is what you're looking at. And so in this case, the h value is positive 2. So then I'm going to also add 2. What's the transformation that's affecting our y values? Minus 3, that we're just moving down 3. Okay, and if we were to write these in words, just so that we get a little review with this, okay, there's a lot of horizontal stuff and only one vertical thing. There's 3 things I would have to say horizontally. Okay, the multiplying by the negative would be a reflection over And then if I have to, I stop and think. The negative is changing the x's. The x's are positive on this side of the graph and negative on this side of the graph. So if I'm changing them from positive to negative or negative to positive, I'm flipping like this, which means I'm flipping things horizontally, but over the y-axis. Okay, so this is a reflection over the y-axis, even though it's changing x. Then x is being multiplied by 1/2. Multiplying by a number is either a stretch or a compression. Because this is happening to x, I'm going to start with the word horizontal. And then I'm going to ask myself, when I take these numbers and I multiply them by 1/2, am I making the numbers smaller or larger? What do you guys think? Smaller, right? If you take 6, you multiply it by 1/2, you get 3. So if I'm making them smaller, I am compressing. Okay. And then lastly, horizontally, there's this addition of 2. Adding and subtracting values is just shifting you on the graph. If you think about your x-axis, if you were on a point and you added 2 to it, you would literally go to the right 2. So we have a shift right 2. And then vertically, we also have a shift because we're subtracting 3. And on the y-axis, if you subtracted 3, you would move down 3. So we have a shift down 3. Okay, so a little bit of review with like the words that you need to use to describe your transformations to give you guys help with that. And now we need to go through and do the work. I'm going to do the y column first because I think that you guys would be able to do that faster. So I'm just going to take all the y values here from the parent function and subtract 3 from them. So that's not too bad. And I think you guys know what to do for the other ones. I think the fractions just sometimes bother us. And so we're going to work on a little bit of that fraction math. So for each thing in the x column, I'm going to take it, multiply it by -1/2, and then add 2. So I need to do -1/2 times whatever I'm plugging in and then add 2. Okay. So the first x value is 1/4. So remember, do your multiplication first, and if you have to, have a piece of scratch paper just for your fraction work, okay? We're not going to do a ton of them, but they show up a couple of times in a different graphs, especially the log and exponential ones. So this is -1/8 plus 2. And depending on how good you are at fractions, some of you look at this right away and say this is 1 7/8, right? Because it's like there were 2 positives and you took away like a fraction of those 2 positives. So you have 1 whole positive and like whatever's left of the fractions of the other ones. If we don't know that, we want to think about 2 as 2/1 and make a common denominator of 8, which would be like 16/8. So when I add these together, 16 and -1 is 15 with 8 in the denominator. And then to understand that number more thoroughly, 8 goes into 15 once with 7 left over. Okay. And again, don't worry about graphing 1 7/8. You just know like it's really close to 2. That's all we kind of want to know, right? Now we're going to go through and do the same thing with 1/2. So I'm going to go back, and this time I'm going to plug in 1/2. So -1/2 times another 1/2 is -1/4. And again, some of you are really good at fractions, and you look at this right away and go, if I had 2 and you took away 1/4, I have 1 3/4. Okay? Others of us are like, what are you talking about? Then we're going to make this into a fraction and make it have a common denominator. So we want to add -1/4 plus 8/4, which is a denominator of 4, and -1 plus 8 gives us 7. If you don't like the way that number looks, think about how many times 4 goes into 7, 1 whole time with 3 left over. So that's 1 3/4. All right, we're going to do the same thing now with 1. So -1/2 times 1 is -1/2 plus 2. So a lot of you are better at like halves. If I have a -1/2 plus a positive 2, a lot of you right away are going, okay, that's 1 1/2 because I had 2 and I'm taking away 1/2. And that's fine if you know that right away. If you don't know it right away, you're going to go through the same process of making the common denominators. And you get 3/2, which is 1 1/2. We're almost done. We get to plug in 2 and 4, and these will actually work out a lot nicer. Because when we plug in 2, notice these 2 cancel. So I'm just getting -1 plus 2, which turns out to be 1. And when I plug in 4, they also have a common factor. So this is -2 plus 2, which ends up being 0. And then remember with your asymptotes, for our exponential functions, our asymptotes were horizontal across the graph like this. So the only thing that moved them was to shift them up or down. Now with a log function, your asymptotes are vertical like this. So what's the only transformation that would move something off of the y-axis if it's vertical like this? You can't reflect it or stretch it. It's already attached to an axis. So what's the only thing that would move this infinitely long vertical line right here? What would you have to do to move it? Yeah, you're right. Translation or a shift, right? Just shift it this way or this way. So there's two ways for you to know where the asymptote goes for your log function. It's going to match your horizontal shift. So that's one way to know. This one was 2 to the right. Okay, so that's where our asymptote ends up. If that doesn't sit well with you, you can literally transform it the same way you transformed the points. If I know the asymptote was an x value of 0, look at what we did to all of our x's here. We multiplied them by -½ and then added 2. Do that with 0. 0 times -½ is 0, and then add 2 and you'll get 2. And so now this asymptote went from an x value of 0 to an x value of 2. So here is my asymptote. The reason this is useful to us is it gives us something to follow, and it also gives us that boundary. We know the log function should only have points on one side of that. Usually the right side, but if it was reflected over, then the left side. Okay? And we did have that horizontal reflection, so we'll see where our points end up. So 1 7/8 is really close to 2, and then -5 is the y-coordinate. And then 1 3/4 is really close to 2 also, and -4 is the y-coordinate. Then 1½ -3, 1 -2, 0 -1. You can kind of see it curving away from the asymptote, and this is a good picture. I see a curve, and I see that the points get closer and closer and closer to my asymptote without really crossing it. So then I can go ahead and draw this curve in, this part getting closer to the asymptote, this other part curving away from it. Okay. Is this okay with everybody? Yeah? All right, so our homework 7 is graphing exponential functions and graphing log functions. So all the transformations are going to be the same. So you'll get practice with that, but you need a lot of practice with your parent functions. If you notice you're missing them because of your parent functions, sit down with me, a friend, something, and let's figure out a way for you to get your parent functions correct, okay? And then make sure you're keeping track of your asymptotes because that's kind of like an extra thing with these functions that you didn't have with your other functions, okay? It'll help you graph them as well, all right? And then tomorrow, we're going to do a review activity.